Okay, thank you and welcome to this session, which title is The Renewable Energy Reality Case Studies. As I was telling to the speakers of this session, I'm very glad because I am very interested to the real experience of this attempt of this huge entrance of renewable energy sources into our energy systems, mainly electricity, but not only. So we have today the session that is shared between Claudia Fieldler. She will give us a view from a modeling point of view concerning the total energy sector in Europe, not just the 27 countries, but also some others. And then at the beginning, we start, as the program says, with Bernard Francois Ben Ahmad. I'm very interested in what he's going to present, because it deals, his presentation deals with the nuclear power system of France, but it is the nuclear power system of Europe, because without it, the European power system will not exist, or would be very different. And then Catherine Kessner goes into the experience of the wind and solar in Germany, correct? And we were supposed
to
solar, yes, the solar, the consumption. It deals with consumption in the final residential sector. That is where we have this solar rebound, something that I learned for the first time looking to your abstract. Very interesting. And we were supposed to have a fourth presentation that has been cancelled, unfortunately. Therefore, we have a little bit more time than the 15-20 minutes allowed at the beginning. So we can enlarge a little bit, but it is up to you to decide within the 20 minutes, 25, how much time you want to dedicate to your presentation. And I will gather questions. I will raise some as well. And for this reason, I leave the floor to Francois Ben Ahmad. We are among economists today. I am an economist. You, Francois, are an economist. You are an economist, as far as I read from your presentation, from your CV.
Yes.
So we will see from the perspective of economists the problem of renewables are raising in the energy, and particularly the power system of Europe. This next presentation is dedicated to France and to its nuclear system, its nuclear capacity, how the intermittent production of renewables is affecting the reliability, I suppose, of the nuclear system. Thank you, Francois. It's up to you now.
Okay. Good morning, everybody. Thank you, Mr. Chairman, Mr. Tavarelli. Thanks for the organizing the committee of this nice conference. I am so happy to participate for the third time. I will participate surely in the coming sessions. Thank you, Claudia and Catherine, for being here to listen to this presentation. So my topic, the topic I will try to answer in this presentation is about the interaction between renewables and nuclear power, especially wind and solar generation. And I will take as a study the French electric system. So what is the motivation of my research? I will begin by talking about the European Union energy strategy that is mainly driven by the need to decarbonize the energy sector. So there was some objectives at the first climate energy package in 2007, and the second one 2014, which fixed the targets for 2030 compared to 99 levels, about a reduction of 40% of greenhouse gas emissions, and selling about renewable energy, and to making its share growing to 27% in total in primary energy mix, and improve energy efficiency about 27%. And just some days before, European Union leaders have just agreed in a new goal to cut greenhouse gas emission by at least 55% by the year of 2013. So that is the motivation of my paper, especially the central role that will be played by renewable in decarbonizing the energy sector. If we talk about power generation as one of the most components of energy sector, if I take the case of France, we can observe from the charts that nuclear energy share in electricity generation in France exceed 70%, whereas wind and solar doesn't exceed 8%. So there is a big share of renewable and a very small share of renewable. And the government is planning for an exponential growth of installed capacities in the coming year. For example, I will show the states of coverage, how many consumption needs are covered by each source. So we see that the solar in blue color and wind in red color doesn't participate enough in covering consumption need of France, whereas nuclear contributes predominantly about 70, 80, 90%, and sometimes, especially in the spring and the summer, more than 100%. That means that France have excess capacity and exports its nuclear power to its neighbors, to Belgium, sometimes to Germany, to England, to Spain, to Switzerland, and sometimes to Italy.
Okay? Not just sometimes, frequently.
Frequently, yeah, I agree with you. So Electricité de France operating the world's largest fleet of nuclear reactors. So you have one company and 58 nuclear plants. So they shut down 2 nuclear plants in Fessenheim in the French-German border, but there is still 56 nuclear plants. So it is the largest fleet all over the world. Actually, maybe in the coming year, the Chinese will exceed EDF. Surely they will exceed EDF. So Electricité de France, which is a public sector, because the government of France has about more than 80% of its participation in Electricité de France, is progressively challenged by the growing market share of renewable energy sources like wind and solar. The more the renewable is growing, the more Electricité de France is challenged. So my research question is that renewable and nuclear energy, can we consider them as a friends, or can consider them as enemies as foes? Okay, so to answer this question, I will just remember the principle of merit order effects, and I published some paper about that, especially in the for the German case. So as the renewable energy sources have priority access to grid, and they participate to the auction price at zero marginal costs, they can replace every other energy sources with higher marginal costs. And at the beginning, they replace natural gas, coal, and now they can replace nuclear in France. So progressively, they are taking market share from renewable, and the figure show this effect, the displacement of other energy sources. So if we take as example the German experience, we have progressively seen a growing of installed capacity. So now there are more than 100 gigawatt installed capacity in Germany, and progressively at the same time we have a program of phasing out from nuclear power plants. So this scenario, can this scenario be possible for the case of France? That is the question. So if I take the case of France, now, actually, we have about 26 gigawatt of installed capacity. So we are, Germany has installed about 5 times more than wind and solar of France. And here there is some graphics showing that there is a correlation, a strong correlation between consumption and nuclear. There is a negative correlation between nuclear production and solar feed-in, and there is a positive correlation between wind and nuclear because they have a seasonal profile. The seasonal profile impacts this correlation. So I will move fastly to show my finding. So I decided to carry out an empirical analysis. So this empirical analysis, I've just take hourly data of load, consumption, of solar feed-in, of wind feed-in, and imports, and especially imports from Germany. And I carry out just a conventional regression using the ordinary least square. And I've showed that there is a clear negative impact because the sin is negative. There is a negative impact of solar and wind on nuclear feed-in. That means that the more the capacity, installed capacity of solar and wind, the more the market share of nuclear will decrease. But this model wasn't quite satisfied quite well because our R squared was about explain about 80% of the variability of nuclear feed-in. So I've decided to add an autoregressive term here, an autoregressive term. And when I add this autoregressive, I make a correction of autocorrelation. So I found that my R squared increased dramatically to attain 95%. And my archaic criterion has decreased, and my Durbin-Watson is approximatively more closer to 2. That is the indication of a good model. So my conclusion of my study is telling one thing: there is negative impacts of renewable. Of solar and wind on nuclear. This impact is also amplified and by the imports from Germany, because Germany has the same problem. And sometimes when the feed-in especially in winter period, when there is a lot of wind coming from Baltic Sea, and Germany in order to to manage these high flows of wind feed-in, they sell it to borders, they export to a neighbor country, and especially to France. So there is a negative impact of these imports, but it is exacerbated by the local productions. Though there is double impacts: the renewables coming from Germany and renewable locally produced. That is the first first result. The second result, we can see that the impacts of solar is much more important than the impact of wind. But we can explain this by the fact that wind comes when the load is so high. When we have a lot of wind feed-in, it comes in season, in winter, especially in winter, when France consumes a lot of electricity, because the heating system in France is based upon electricity, in contrast to Germany. So we have sometimes we can consume till 100 gigawatt to cover our needs. So the wind comes in the good periods, when we are in big need of this wind. So its impact is still negative, but it is less important and less pronounced than the solar one. However, the solar feed-in comes in the periods of the demand electricity demand is so low, so the impacts will be much stronger and much pronounced. That's why the results of the coefficients of solar is much more important, and that is my final sentence. Thank you for hearing me. Thank you.
Okay, thank you. Francois, I do not see questions from the floor from the participants. I ask you a question about your presentation, and but at the end, you started you with your statement: are they friends or enemies?
Yes.
Now, what is the final conclusion about it?
They are enemies. Enemies. Look, Professor Tabarelli, it is a Catholic marriage. It is a Catholic marriage. There is no divorce, but okay, this is unhappy marriage. Okay. So they will survive. They will survive. The two components will be here, but it's not a happy marriage.
Yeah, another point. We in Italy, we do not have nuclear capacity, despite the fact that we import a lot of power from France. We have a lot of CCGT running on gas. They are very flexible.
Yes.
So instead, you are based on nuclear capacity that is so base load, flat, rigid in anticipating and adapting to the unpredictability of solar and wind. How do you see the possibility to, with this tripling of or more, I didn't understand, of wind and solar, with this rigidity you have on nuclear?
Yes, I agree with you. So I will make a comparison between Italy, Germany, and France. So indeed, in Italy, you have a capacity of gas plants, natural gas plants, which give you more flexibility to adapt. So the natural gas plants work as a backup to renewable. Where there is no sun, no wind, you switch on fastly your natural gas plants, and the problem is resolved. In Germany, it is the same case, because I see the last data. Natural gas, because of CO2 emission, European Union emissions trading scheme worked good in good time. So now the natural gas plants is much less expensive than coal plants. So Germany is progressively growing its capacity in natural gas, and we can never develop massively wind and solar if we haven't enough capacity in natural gas. So it is the lesson learned from Germany, and it is the lesson learned from Italy. So now France, they are, I don't think so, huh? The leaders of EDF, we are so flexible. We can make the load follow in, so we can switch on, switch off, switch on to follow the load. So we can be so flexible as a natural gas flat. And honestly, I don't believe in that, because nuclear power is not enough flexible as a central gas plant.
Yes, yes. But do you think that the targets of the French government, it announced last year to to phase out nuclear towards 2035 might be achieved?
Yes, because they are planning to shut down about 15 nuclear plants, because when they reach 40 years, you have two options: to extend or to stop. So they will wait all the nuclear plants to attain their age of 40 years, and they will stop them. But it is a political decision. So there is, for example, President Macron is telling to Green Party, yes, I will shut down the nuclears, but he tells to the right wing, no, we will not shut the right wing. So I listen, I hear that they have projects of building new nuclear plants, about 6 new nuclear, about technology of EPR, like the projects of Hinkley Point in England, like the projects in Finland, and like the projects in China. So there is a nuclear, they have a lot of supporters in France, because it is a big industry. But there is the civil society, the Green, as pushing to phase out, or at least to make less, to make the share less important, about 50%.
Okay, Francois, times for...
Yes, I agree with you. Thank you so much.
No, yes, that is my fault that I'm so interested in what's going on in France, because it is a pillar of the power system of Europe. Without nuclear capacity of France, we cannot have an electricity reliable system in Europe. So now we have to move to Catherine Kestner. Catherine, excuse me if I make it wrong. You are an economist as well, if I read well. So yeah, we move sharply away from big power generation plants like those of France, and we move to one of the key topics of the European energy transition, that is distributed generation, and concerning solar in particular. And please go ahead with this concept of solar rebound and the evidence from Germany, the importance of this industry and this event in Germany, that is the leader of a transition and the market where there have been the most interesting developments in the recent years. Thank you, Catherine.
Well, thank you. I hope you can all hear me and see the slides.
It is perfect, thank you.
Perfect. Then, yeah, let me also just quickly introduce myself. You already introduced me so nicely. So I'm Katrin. I'm a PhD candidate at the RWI, the Leibniz Institute for Economic Research. And I'm very happy to be here today and to get the chance to present this work actually for the first time today. And it's joint work with my colleagues Manuel Freundl, Stefan Sommer, and Colin Vance. And it has the title Photovoltaics in the Solar Rebound, Evidence for Germany. Yeah, as a quick motivation, as we all know, carbon emissions in the electricity sector should be reduced. It's one way to tackle climate change. And in Germany, the expansion of renewables has actually, because of that, already been supported for a long time. So since 2000, through this Renewable Energy Sources Act. And the feed-in of renewables is promoted via so-called feed-in tariffs. And one technology that is especially interesting for our research are photovoltaic panels, because they are actually not only installed by companies, but they can also be installed by private households. And in Germany, there are actually at the moment, or as of 2019, more than 1 million rooftop solar installations from private households. However, behavioral economists are quite often concerned about some adverse behavioral effects that may happen when private households do energy efficiency improvements or do some environmental friendly investment. For instance, you may all know this classical rebound effect, which states that when private households do some energy efficiency improvements, so for example, they buy more energy efficient household appliances or improve their fuel efficiency of a car, that leads to energy savings, but households may have this adverse effect that they start using then the appliance or the car more often, and thus there's a partial offset in the energy savings following the energy efficiency improvements. And that can be explained through price effects, but also psychologically through this moral licensing, so that households feel legitimated to do something bad after they did something good.
Sorry,
now you may wonder, what does this have to do with? Yeah.
Catherine, sorry, can you spend a little more time on this rebound effect, please? Because you call it a classic rebound, solar rebound effect that I wasn't aware. I apologize. And it is extremely interesting that it is a subject of interest and of research.
Of course. Yeah, so I mean, I call it classical because then to make the distinction between the solar rebound, which I will then explain. So the classical rebound explains that, so from an economist point of view, let's say a household buys a new washing machine, which is now more energy efficient than the previous one. Then one washing cycle becomes cheaper for a household because now it uses less electricity. So a household needs to pay less for the use of this washing machine. And since now this washing cycle is cheaper, this may be an incentive for households that they feel like they can use it more often because they don't need to pay as much for it as before. And that's this rebound, because so electricity consumption doesn't decrease as much as it could, but it rebounds, it goes up again a little bit, but it doesn't have to fully offset the savings that are possible. But so that is the idea behind this classical rebound. Exactly. And now, so there is also a thing which is called the solar rebound effect. And that is that came up in the theory from Oliver et al. And there the idea is that so households usually they consume electricity and take that from the grid and pay a certain amount of money, so cents per kilowatt hour for that. But now when households own their own solar panel, they replace this electricity consumption from the grid with electricity from their own solar panel. And the solar panel, even though they make this investment, it then, as we heard already earlier, it produces electricity with marginal costs of 0. And therefore, when the household then consumes this electricity, the household doesn't have to pay anything for this electricity at the margin. And therefore, the average price that a solar household pays for electricity decreases. And this in turn could then mean that households, because they now pay less on average for the electricity, that they have an incentive to increase the electricity consumption again. And that's what is called a solar rebound. And there is already actually some empirical evidence on that from the US, where there are no feed-in tariffs, and from Australia, who also have feed-in tariffs. And the authors of these studies find solar rebound evidence of about 15 to 21%. Now you may still wonder, why is this of interest for us? Why is the solar rebound important? What does it mean? And why do we also in our research now pose this question? Do German solar households change their electricity consumption after installing a PV panel? So if solar households in Germany change their consumption and if they increase it, so there is a solar rebound, this means that this potential of PV panels to reduce one-to-one this electricity that is taken from the grid is diminished. And renewable energy, or photovoltaics, they are there to increase the share of renewables in our electricity sector. But when then in turn, households again increase their consumption, this positive effect of the renewables is partially offset, because it may also be the case that this increased electricity consumption is again partly covered by fossil fuels. And even though these are subject to the European emission trading system in Germany, there's still a reduced local environmental benefit from the PVs. And that's why we're interested in this topic. I will also give you a quick background on photovoltaics in Germany, because this is important to understand how we estimate then the solar rebound. So when German households buy a photovoltaic panel, they install that, and then especially in earlier years, which are also then of interest in our study, these households, they first self-consume a share of this PV generation, and that is on average about 30% for German households. So they consume a share of about 30%, and only this remaining part from the solar generation is then exported to the grid. And for this export to the grid, households then receive a fixed feed-in tariff for 21 years. And this level of the feed-in tariff is fixed according to the date of installation. And as I will show you, the feed-in tariff used to be much higher than the average electricity price. So here you can see the development of the average electricity price in Germany, here in the black line. And you can see it is below 30 cents per kilowatt hour for a long time, or still, but it reaches now the 30 cents. And the feed-in tariffs, they are here in the gray dotted line. They were as high as almost 57 cents per kilowatt hour in 2004. And this only changed so that the feed-in tariffs became lower. This changed between 2011 and 2012. So if a solar household in Germany installed, for example, a photovoltaic now in 2004, and they fed the electricity into the grid, they received this above 50 cents per kilowatt hour for feed-in, and they received this 50 cents per kilowatt hour for the next 20 years. So during this period, there was a very high incentive for households to feed in a lot of electricity into the grid. And now this period is interesting for us because it's also the sample period of our data, because we use the panel data set, which covers 12 years from 2004 to 2015. And we use the German Residential Energy Consumption Survey, the GREX, and it's composed of 7 surveys where we always ask the same households. And we know their socioeconomic data, we know about their PV ownership, the date of the installation, we know their grid electricity consumption, the marginal electricity price, and also their total costs. And so we have this relevant information for about 8,000 households. And of these, 358 install a photovoltaic in the sample. So we have a share of solar households of 4.5% in the sample. And that is actually quite similar to the share of solar households in Germany at the end of our study period, which is 4.8% in 2015. Now, what is really important is that we don't have any data on the solar generation and also not on the total electricity consumption of solar households. So we only have this grid electricity consumption, but solar households, they have a composite consumption of the self-consumption of the PV and the grid electricity consumption, but we only observe this grid electricity consumption. And that is important, as you will see in a few minutes. And then we also use further data because we need 2 instruments for our endogenous variables, because we have this PV indicator in there, which is very likely to be endogenous because the PV installation may be driven by determinants that we cannot observe, such as environmental attitudes. And therefore we use the number of photovoltaics that are installed within a zip code area as an instrument. And we take this data from the German transmission system operators. And it's the idea behind that is peer effects that were found by Bollinger and Gillingham, that so when households see that in their area there are a lot of photovoltaics, they also are more likely to install a PV as well. And then the marginal price that we use in our model is also endogenous, because in Germany, households can choose their own electricity tariff. And therefore, we use the sum of regulated price components as an instrument. So the price is also partly made up of a fixed component, and we can take that as an instrument for our price variable. Okay, now I also need to talk a little bit about the theoretical framework, because this is important to understand how we estimate the solar rebound. As I told you earlier, so from solar households, the total electricity consumption is then made up of here what you can see in equation 1, the grid electricity consumption plus this share of self-consumption from the photovoltaic generation. And we call this share theta. And as I said earlier, in Germany, it's about 30%. Now the solar rebound states then, how does the total electricity consumption of a household change when a photovoltaic panel is installed, or in the continuous case, when solar generation increases. And so therefore, in here equation 2, when we take this derivative, we can see that the solar rebound depends on the change in grid electricity consumption and on this share of self-consumption theta. And there you can see that if the grid electricity consumption remains unchanged, we know that there's a solar rebound which is still equal to this theta, or is bounded from above by theta, because we know that households first self-consume, so this share is definitely fixed, and then if the grid consumption remains unchanged, there is a rebound because altogether total electricity consumption increases. And that is important for us because, as I said, we only observe the grid electricity consumption, and therefore we want to test this null hypothesis, whether grid electricity consumption changes after a household installs a photovoltaic panel. And if we cannot reject this null hypothesis, this means that there is a solar rebound because households first self-consume and then they have the rest that they take from the grid. And if that is remains unchanged, the total consumption increases. And that is then by this share theta. Okay, so to test this null hypothesis, we estimate a dynamic panel model. So there we have the grid electricity consumption, or the logarithm of the grid electricity consumption here as dependent variable. Then we have our PV indicator, PV, where the coefficient beta is our coefficient of interest, with which we can then tell whether our null hypothesis can be rejected or not. We have the marginal price, and we have a set of socioeconomic variables. We have year fixed effects that account for a general trend in the electricity consumption, and also individual specific effects to account for unobserved heterogeneity. And then we estimate a dynamic panel model. So we also have this lag dependent variable in there. And that is because we know that the current consumption level of households highly depends on the previous level of electricity consumption of households. And because there's a high inertia also in the appliance stock adjustments that households can make. So they cannot quickly just replace all of their fridges and everything. So there's a high correlation. Of course, when we have a dynamic panel model, we cannot simply use fixed effects methods. So we apply the system estimator by Plandell and Bond, where we have the instruments on the one hand for our price and PV variable, which I mentioned earlier. And we can use these internal instruments, so the lagged differences of the dependent variable as instrument for this endogenous lag dependent variable. Okay, and then these are our results. We have two specifications actually, where we on the one hand just have the PV indicator and the price separately in there. And then in the right column, you can see that we also interacted the price and the PV variable, because we were interested in knowing whether maybe households that install a photovoltaic are more aware of electricity prices because they are more aware of the topic in general. And in both specifications, we include the socioeconomic controls and also the year dummies. Now let me start with the interaction. Here you can already see it is not significant, so we don't find any evidence that solar households have a higher price elasticity. And also our coefficient on the PV dummy is in both settings insignificant. It is negative, but it is insignificant. So we don't find any evidence for a significant change in the electricity consumption from the grid of solar households. So this means that we cannot reject our null hypothesis. So we find that it seems like households after installing a photovoltaic don't change their grid electricity consumption. And this in turn means that there is a solar rebound, which is bounded from above by this share of self-consumption theta. And as I said earlier, it is on average for German households 30%. However, let me discuss this a little bit, because we think that it is unlikely to be really 30%, but it could actually be lower for these households in our sample, because during this study period, as I showed you, the feed-in tariffs were really high. And so households had a strong incentive to really maximize this feed-in of the solar generation. And so if they actually self-consume 30%, they forego a remuneration from this feed-in of about 680 euros per year. And that is almost as high as the average electricity costs of German households. So therefore, some households, at least, they may have this incentive that they feel like they can shift their consumption maybe from the day to the evening, so that while the solar panel produces a lot of electricity, the households don't consume that much. And so the share of self-consumption is lower, and thus also the solar rebound. So just to conclude, our study indicates that households that install a photovoltaic, they don't seem to change the grid electricity consumption. That means that there is a solar rebound, which could be theoretically up to 30%. Even though we don't find that solar households have a higher price awareness, we still think that they are aware of their feed-in tariff and therefore may have this incentive to maximize the feed-in and reduce the share of self-consumption, and thus that the solar rebound is smaller than 30%. And so since we find some evidence for this small rebound effect, there's some diminished local environmental benefit from the photovoltaics because households still increase their total consumption. Yeah, otherwise that's it. Thank you. And happy to hear your questions.
Thank you, Catherine. Thank you, Catherine. Are there any questions? I do not see any of them. And as always, I raise a couple of points. The first one is, again, it stems from, my question stems from the fact that I'm not so aware of this problem. You investigated the fact that there might be some relationship between photovoltaic and behavior of the consumers. So you were expecting, I didn't understand well, you were, some should be expecting a sharp reduction in consumption from the grid when they have a PV plant. That is the problem. So you expected something that you didn't see in reality.
Well, not necessarily. It's more that theory actually suggests that we expect an increase in the consumption because the electricity consumption on average becomes cheaper for households. And then there's this rebound that people may increase their consumption by quite a lot. Yeah. Okay.
So it is the contrary. So given the fact that they produce their own electricity at zero cost, or at least, yes, a marginal zero cost, we should be expecting a higher consumption that you didn't see from your research.
Well, we see, that is the thing, we see that the grid electricity consumption doesn't change, but we know that households first consume parts from their generated electricity from the PV. So we see that somehow there must be some increase. We also observe that households increase their total consumption. So there is a rebound.
Okay, so yeah. The final point, when you when you point out that the slightly diminished local environmental benefit, but does it mean that you are disappointed about the environmental benefits? That means that all the feed-in tariff, your subsidies you gave, Germany gives to PV is exaggerated.
No, well, it means that we want, of course, and that's the goal, that the local environmental benefit is as high as possible. But yes, that's what we find. We know that if there is a rebound, it means that the total electricity consumption is again increased. And that's what we don't really want, right? Because we want, in general, we want the electricity generation to be carbon emission friendly. Yes. And we also want that households decrease their consumption. And so now when they install this photovoltaic, that is already the first, it's a good step. But then if they in turn increase their consumption, the photovoltaic generation doesn't one-to-one reduce the household electricity consumption that is covered by grid electricity that is maybe covered by fossil fuels. So okay, there are still fossil fuels in the consumption, of course, of those households. And of course, the fossil fuels are subject to the ETS, but still, like, the local benefit in Germany, that is then diminished. So that is a small disappointment, but we still think that it's not that high because the rebound is not that high. But it's something that, yeah, must be incorporated when thinking about photovoltaics.
Okay, another, the final question is, I saw from the data gathering, you have some problems because from what I know, differently from Italy, where we have almost 800,000 PV plants, not only rooftop, but you do not have a specific center or institution that has all the information concerning each single PV unit. It doesn't exist in Germany, this kind of, because in Italy, we have GSE, that is an institution that has all the information concerning these plans. Yes, it seems that in Germany there is no the official statistics concerning all this capacity, all these 1 million units.
Well, there's information about the photovoltaics and how many are installed and where. But the thing is that we want, of course, also the socioeconomic data in there, and so that's why we need this information from the household specifically, because it's we cannot otherwise connect that with the official data on photovoltaics, and so therefore we have the information from our surveys, from our own surveys. Okay. But there we don't know.
This German residential energy consumption survey, is it done from the official statistical office of Germany?
No, that is done by us, by the RWI, by the Economic Research Institute.
But which is the main source of PV information in Germany?
Well, there would be, I think, on the one hand, so the transmission system apparatus, and then the Federal Network Agency. Okay. That has, you have to, when you install your photovoltaic panel, you have to register it at the Federal Network Agency, and there's the information about every single PV.
Okay. Thank you, Catherine. No, Françoise, go ahead. Turn on your microphone.
Thank you so much for a nice presentation, Catherine. So my question is the following: what are the policy implications for this rebound effect? So the government will see that the more it subsidizes installing of PV for the household, the more household will consume electricity. So is there a consequence about the electricity market design, especially in tariffs and in incentives to curb this behavior?
Yeah, I suppose, well, it is already changing, but the thing is that, so the feed-in tariffs were very high in early years. So that might be something where one could say, okay, if they are a little lower, then this incentive is gone for households, right, to maximize the feed-in. But it is interesting actually also to now, excuse me, to look at this follow-up, because now it is changing in Germany, right? Because now households can actually more and more store the electricity from the photovoltaic and have this battery storage system. And then that again changes a little bit the whole implications. And we think that the rebound is then actually even smaller. But in general, it is that the feed-in tariffs were something that could be changed.
Okay, thank you, Catherine. Thank you, François, for your question. Now it is the time of Claudia. Claudia Fiedler is going to present a paper concerning the modeling of the European energy system and the entrance of this renewable capacity and the production. She's again an economist, but I would say an econometric expert. And so we have so far problematic issues concerning renewables. I suppose you, Claudia, instead you are going to speak more positively about renewable energy sources in the future of a European energy system. Thank you, Claudia. It's up to you now.
Yeah, thank you. Yeah, it's my presentation is about the final energy consumption and not about the renewables because of switching the issues. So I share my slides. Can you see the slides?
We see Monaco di Baviera.
Yeah, okay. Munich, yes. The first slide, yeah. Yeah, thank you. I'm glad to present my topic here at the virtual conference. My topic is modeling transformation pathways for the final energy demand using timely and spatially resolved sector models in the European countries. But first of all, I would like to introduce myself and the institute I'm working at. My name is Claudia Fiedler, and I studied geoinformatics And now I have been working at the Research Institute FFE for 5 years now. So the FFE has been working independently for more than 70 years now on energy technical and economical topics, like you can see here on energy system integration, energy efficiency, digitalization. And the competences of the FFE include the IT modeling and the data analysis, which you can see in the next slides, the project coordination as well, and other competences. We are 80 employees in Munich at the institution. And yeah, here you have an impression about us at the FFE. My topic I present is embedded in the project Extremos, which is funded by the Federal Ministry for Economic Affairs and Energy in Germany. And in this project, we develop and enhance and apply different models at the FFE, and we model the energy system. So we combine in the scenarios the storylines, like here on the right-hand side, and the storylines which are on a qualitative basis, and we combine them with the quantitative models. So we get a whole scenario about the energy system. This is the scenario I want to present today. Does not respect the climate targets, the national and international targets, and is purely economically driven. Politically and socially, the situation in Europe is changing for the worse. So it's a quite extreme scenario. It's not a climate protection scenario. And this scenario we model with our tool chain, like on the left-hand side. We model the final energy consumption in 4 sector models, which I want to present in the following. And we combine them with the renewable energy models to energy system, whole energy system model. So for modeling the energy system in Europe, it is necessary to get the load profiles of the sector models in on NUTS 3 level. That means on district level, with a time resolution of 1 hour, and that we model for different scenarios until 2050. And today it's about the scenario I explained. So for each of these 4 sector models, we have like this here, a flexible structure, but they are all quite similar. So the structure is about 3 main columns: the final energy consumption per country, and we develop in the final energy consumption until 2050. Then on the second column, the regionalization, we distribute the final energy consumption to the NUTS 3 level. And then with the last column, the load profiles, we distribute the final energy consumption to a timely dependent load profile. So we have for each column input data and parameters which we can change, and we can change the logic. So we can model different versions about different versions of scenarios. So we have 4 sector models: the industry, the transport, the private household, and the services model. All models are based on the input data from the energy balances from the European statistics from Eurostat. They have a resolution of a country, of main energy sources and sectors, and also sometimes in branches of the industry, for example. But for modeling, the for modeling the final energy consumption in such a detail which we want, we need also the application like space heating, warm water, cooking, process heating. And that's why we split the European energy balance down to the application. So we have finally the application-based European energy balance. On this balances, the sector models are based on. You can, if you want to look more in detail into these data, you can download these data on our Open Data website, on our Open Data portal, on the link opendata.ffe.de. So now we switch to the first column, the final energy consumption of the model. Here you can see 3 steps: the baseline development, the energy efficiency, and the fuel substitution. These 3 steps you can find in all our sector models. And so we can model the final energy consumption until 2050. The baseline development in industry is based on each country's gross value added, the energy intensity, excluding efficiency measures, and the production tonnage. The baseline development in the transport sector and in the buildings sector is based on the population development until 2050 for each country, and the transport capacity and the energy demand per capita in these sectors remains the same. In the next step, the energy efficiency are like measures in the cross-section technology and process-specific measures. In the transport sector, there's a technological progress like the specific consumption is decreasing until 2050 of the vehicles. And in the building sector, the insulation is the energy efficiency measure. So we assume a renovation rate of 1.1% annually. The last step is the fuel substitution. In the industry, we have different measures, but these are not included in this scenario because it's quite conservative. In the transport sector, there we use a direct electrification in the case of passenger cars, in which the internal combustion engine are exchanged by electrical vehicles. And here the indirect electrification also is excluded because like hydrogen passenger cars or trucks, because this is also a step in another scenario.
I cannot resist, Claudio, to ask you how many electric vehicle, full electric battery vehicle do you expect in Germany in 2030 or 2050?
Yeah,
if you can tell me.
Yeah, it depends on the two-way NDP in this scenario. Sorry,
what is a TIWP?
The 10-year network direct program. Thank you. Yes, this conservative scenario we use for the direct electrification of the passenger cars.
Okay.
Yes.
Because we have in Italy, but as everywhere in Europe, sharp debate about electrification of transport, let alone the other sectors. So it is, I cannot resist to ask you some assumptions that you make because they could reflect your view and the view of your institution concerning penetration of electricity in the final
yeah. In Italy, it's also assumed the data from the TYNDP. So it's also quite conservative in this scenario I present.
Okay,
yeah.
Okay, thank you.
The fuel substitution in the building consists in the installation of heat pumps. And according to a country-specific market analysis from today. Now I want to show you a result about the final energy consumption in Europe, for example, for the private households. So in this scenario, we get on final energy consumption, like on the left-hand side, from more about 3,500 TWh. And it reduces until 2050. On the second diagram, we can see the share of energy carrier. And there we can see that the heat pumps, the electricity from heat pumps increases until 2050, and the gas and the oil consumption decreases until 2050 because of the installation of heat pumps. The share of application you can find on the right-hand side. There you can see that the final energy consumption in the space heating application decreases because of the insulation in this sector. So you will have an impression about our results. This result we have for also the other sectors and also for each country. Now we switch.
Claudia, sorry, I was asking who are the other three countries? I suppose Switzerland, Norway, but I saw you are going ahead with a map. Please go ahead.
UK, Switzerland, Switzerland, Norway, and United Kingdom. Sorry, yeah. Now we switch to the regionalization. The regionalization is also sector specific. And on the left-hand side, you can see the final energy consumption per square meter for the sector industry. The industry final energy consumption is distributed by emission data and industrial sites, but only in the process application in energy-intensive branches. For cross applications in non-intensive branches, we distribute the final energy consumption according employees and the population. So you can see on the left-hand side, for example, in the north of Spain, that there's a lot of consumption here in this area because there's a lot of industry in this area. And whereas in the map of the final energy consumption from private households, you can't find such a great final energy consumption here in the north. But of course, in the capitals of the countries and in population density areas. The final energy consumption of private households is distributed by the population, and in services it's distributed by employees, but also we use the heating structure, for example, in the share of energy carriers per NUTS 3 region. And we weight the final energy consumption by heating degrees. For example, in the north of Italy, we need more final energy consumption than in the south because it's colder. So we shift a little bit in the north by the weighting by the heating degree days. For the transport sector, we distribute the final energy consumption via vehicle quantities and the population. And if you want to see more about this, you can go to our open data website and get more information about this. So
But Claudia, is it free of charge?
Yes, it is free of charge.
Fantastic.
It's open data, yes. So we going to the load profiles. Here's some insights into the load profiles because we use around 50 load profiles in the sector models. Here you can see the temperature dependency in the application space heating. You can see the heat consumption of 1 year in Munich in the year 2012 in the application space heating. So we can see in the winter we need more heat than in the summer. And if we switch to Oslo, you can see that we need there more heat than in Munich. And if we compare it to Napoli in the south, there we need less heat than in Munich and Oslo. So this is about our methods. And now I'm going to the results. Here's the final energy consumption for the 30 European countries in the Q scenario. So the final energy consumption decreases by 20% until 2050. And if we look at the industry sector, the increase in gross value added and the concurrent energy efficiency measures keep the trend at a similar level. If we look at the services, the final energy consumption decreases until 2050 because of the insulation and the installation of heat pumps. Also for the private households, and the transport sector decreases as well because of the energy efficiency measures and the fuel substitution. If we switch from the final energy consumption to the electricity consumption, we see a diagram like this. In Europe, the consumption of the electricity increases about 15%, and the share of the sectors are changing in the direction to private households and services and is decreasing in the industry. In Germany, we have, of course, a lower electricity consumption than in Europe. And the share is quite the same, but the industry sector has more, has a greater share than the one in Europe, because in Germany we have a lot of industry. So if we switch to the regionalization and load profiles once again, so we can here see the sector-specific results. If we are going to Stockholm in the north, it is a populated region, and thus the average week in this area, you can observe more private household and services final energy consumption than in the industry. If we switch to another region here in Västra Götaland, which is an industry characterized region with paper and chemical industry, you can see that it is the load profile is more into the industry. So let us switch to the temperature dependency of the load profiles. Here's the load profile now, the weekly average of Munich. So you can see that it's a seasonality in Munich because we need more more electricity consumption in the winter time than in the summertime. That is this seasonality becomes stronger in Oslo. So here a stronger seasonality. And if we look to Napoli, here it is a moderate load profile and with a raise in the summertime because of the cooling applications. So these are the insights on the results, and now I'm switching to the conclusion. We have a final energy consumption which is sector, energy carrier, application, and branch specific, with a spatial resolution of NUTS 3 and with a timely resolution of 1 hour. The heat demand is temperature dependent, and thus we can compare the different European countries with one another because of the characteristic of each country. And we have the possibility of making the development of individual technologies in the future. So what we are doing in the next step of the project, we want to model a climate protection scenario through further measures, which I mentioned in the method section. And we model the European energy system with further extreme scenarios. For example, the price drop of photovoltaic system until 2050. Yeah, and if you want to see more about the project and the results, you can go to our open data portal where you can find the data with an open license.
Okay, thank you. Grazie, thank you, Claudia, very interesting. I have also for you a couple of questions beyond those that I already made. Are there about concerning input data? Do you consider different scenarios also for prices? And when I say prices, I suppose energy commodity prices like oil, coal, also CO2 prices, electricity prices. What is the approach concerning prices or tariffs as well?
Yes, the prices are modeled in the energy system model and not in the sector model. So the sector model, the results of the sector models are the input data for the energy system model. And the energy system model is a model which is linear optimized by costs. Mm-hmm. And so there the costs and prices are integrated. And with the energy system model, you can the net, for example, and the oil and gas sites are investigated, and also the renewable.
Yes, therefore, is it an optimization model, yours? Is it an optimization model?
No, my model is not an optimization model. The energy system model in the next step is an optimization, linear optimization model.
Okay, and listen, another point, are there information concerning CO2 emission or particulates or other pollutants emissions from the model? Or do you consider do you think that in the future you will consider also pollution?
Yeah, about this pollution, we will make a new examination. So when we model this like I showed, and then with some pollution factors, we then can calculate the pollution.
Okay, but I didn't understand from the beginning. because the data are open data for we can access it, but who pays for all your work or your activity? Do you sell the scenarios also to some companies, to some clients?
Yeah, the project is funded by the Federal Ministry of Affairs and Energy in Europe. So we have to publish our work, and also we publish some data of our work.
Okay.
So that's why we yeah.
Okay, thank you very much.
Put the data on the open data portal. Not all, but a few.
Okay, Francois, please go ahead. Turn on the microphone.
Yes, okay. Thank you, Claudia, for a nice presentation. So you were quite optimistic in your scenario. That is, there is a decrease in energy consumption. So it's quite promising. We hope so. However, you have said that the electricity consumption will increase, except for Germany. So if the electricity consumption will increase, how can your model take into account? That means that we should install new capacities to answer this new demand. Okay, so we are in need of new capacities.
Sorry, once again, please. No.
Okay, so, I've said that. Okay, your scenario of decreasing of energy consumption globally, the global energy also, okay. However, you have said that electricity consumption will increase in Europe.
Yes.
Okay, except from Germany. So for the countries where this electricity consumption will increase, how can they afford this? How can they found the electricity they are in need of? Should they install new capacities, or should they import from Germany, or what is the solution for them, for these countries?
Yeah, this difference, I think that you mean is a result of the installation, for example, of heat pumps. In some countries, there is a greater installation of heat pumps than, for example, in Germany, because this is a result of the market analysis, of the current market analysis. Also in the scenario, it is like that the population, the results are according to the population. If we have positive population development, we need more electricity. So in some countries, the electricity is higher, and in some countries it's lower.
Francois, they are producing scenarios. It depends on, since we are trying to do the same with my company, in my company, we are mixing altogether different hypotheses. And at the end, we are trying also to understand if we can reach the targets, the final targets of decarbonization, that is the main one for all of Europe. Now, we have to close. I try to summarize in few words. Francois Ben Ahmad has taught us that the two main sources of electricity, I would say in France, but to some extent also in Europe now, are enemies. That is, nuclear and renewable, at least force intermittent, are enemies. They do not behave perfectly together. And this is going to be a major issue in the future, in the next few years. Katrina Kastner showed that there is this solar rebound effect, this rebound effect on electricity consumption in Germany. That is very interesting. Therefore, we do not have such huge environmental benefit thanks to solar, because there is an increase on consumption, relying on the grid that is absorbing electricity produced with fossil fuels. And then Claudia, what I understand from Claudia, the interesting point is that we need scenarios, because the uncertainty concerning the future of the energy system in Europe is going to be, I do not want to use the word worsened, but it is going to be very complicated. And therefore we have to understand the different possibilities with strong penetration of renewable, or with electrification, and with more energy efficiency. Thank you very much. François, je l'attends toi en Italie la prochaine fois.
Avec plaisir, avec plaisir. Avec plaisir.
Très intéressant. Pour favor, vous devez faire avoir votre présentation.
Oui, je vais vous l'envoyer, je vais vous l'envoyer.
Merci beaucoup. Now,
I will send the paper up. I will send my presentation to Claudia, to Catherine, and to you.
Exactly.
It will be a great honor for me. We will share our presentation.
Now I'm going to try in German. Vielen Dank, Fräulein, den Doktor, und ich erwarte Sie in Italien nächstes Mal. Ich hoffe, nächstes Jahr. Vielen Dank und fröhlich, not remember. Anyway, grazie mille, vi aspetto in Italia, ci vediamo a Roma o a Milano la prossima volta. Grazie mille.
Grazie mille.
Sende mir bitte seine Aufstellung, seine Artikel. Grazie mille.
Thank you very much.
Thank you.
Bye-bye.
Bye.